Good afternoon, good evening. On behalf of SP University of Boumerdin Student Chapter, I would like to welcome all of you to the fourth session of the TECHLOG training. My name is Nabil Awidat, a Master of Petroleum Engineering student at the University of Boumerdin in Algeria, and I will be your moderator for today's session. So today's session, geomechanical properties evaluation using the TECHLOG software, and will be delivered by Mr. Nweze Innocent Chukwudi. Mr. Chukwudi is a petrophysicist at DGOID Integrated Geosciences, a technically motivated, adaptable, and responsible petroleum and gas engineering graduate from Port Harcourt University with interest in reservoir characterization and geomechanics. Having a methodical approach to work and a strong drive to see things through completion, in his current job, he has been involved in the full development plan as regarding bidding for an oil and gas field. So before we start, I would like to remind you to keep your microphones muted and to drop your questions in the chat box. So Mr. Nweze, the mic is yours.
Thank you very much and good day everyone. Welcome to today's section of virtual internship, software internship. It's been good working with you guys. I really appreciate your consistency in making this internship a success, which will be coming to an end today. So please, I would like you now to hit up the chat box to tell if I can be heard from your own end. If I can be heard clearly, I need to adjust my mic. Please, I'll need to get these reactions from you guys so that I can further on the training. Thank
you. Sir, if you can just raise your voice a little bit.
Just let me adjust my mic. Just give me a little while. Okay. Hello, can you hear me now? Hello? Please just give me your feedback on the chat
yes,
box.
it's clear. Yes, it's good.
Is it clear now? Please, I don't want just one reaction.
Yes, we can hear you.
Let me know if it's clear. Just hit up the chat box. I need other participants if you can hear me. Okay. I think I will go on with this. So once more, you're welcome to the last section of our virtual internship. And I trust that this will be the end of this internship. And by the end of today, you'll be receiving your assessment from the organizer of this internship. And to top up my question bank so that it can actually work. So I believe our meals assessment as regards these sections, the sections treated so far in the internship. Once more, you're welcome. Now I'm going to go straight to what we have for today, and I'll be going straight to our software. But before I go there, let me just show us one or two things.
Sir, please just repeat because you got disconnected earlier.
Is that was disconnected?
Yes, you got disconnected. So if you can just repeat the last information.
Okay. I said the organizer of the internship is going to send across to us assessment that is meant for this section, for the past sections of our training, that are the three sections that have passed, and that of this one I'm to treat today. So I believe that the organizers do have our emails and our contact on how they can get across to us so that we can be able to get the assessment that have been set for this particular training. Now, to continue from where we stopped, I'm going to take us through what we've done so far. That is, we actually started with how to import our data, how we can bring in our data in our software through our import buffer from our software, after which we actually went through our importation of our well deviation data or our survey data, which I showed you, which is somehow different from importing your well logs. After that, we actually looked at our wells, our well log through our data imaging. We brought in our well log, we brought in 4 sets of well log, we brought in our GRO well log, we brought in our resistivity log, we brought in our density log, and we brought in our neutron porosity log. All these logs we brought in so as for us to be able to actually interpret, do a quick look evaluation of our reservoir. Now, this is just our log view, how it looks like. Now, this, when we imported our GRO log, we actually brought it in and we did some conditioning on it. Now, we also configured our density, our resistivity log, which we also did for our density and our neutron porosity combined. After this, we made some adjustments in the sense that we showed how we can adjust the unit or the scale of our logs. So we've done that. Now, we also did activity computation where we went to our data, we went to our reference and coordinates, and we checked how we can actually convert from our measured depth to our total vertical depth SS, which is subsea, or our total vertical depth MD, that is our mean sea level. And so we actually did all that activity computation. Now, I actually showed us on how we can carry out some plots, GRO plots to determine some of the parameters we need for our estimation. GRO plots are like when we're estimating for our shear volume. For us to get our gamma ray index, we say our gamma ray index is equals to our gamma ray log minus our gamma ray minimum, that is our gamma ray shear, our gamma ray sandstone, all over our gamma ray sandstone minus our gamma ray shear, which is our gamma ray maximum minus our gamma ray minimum. So we check that, and for you to get your maximum and minimum, you can do that through your histogram plot or your GRO cross plot. Now, these are just that. Now, I also showed us how we can go about our zonation, how we can create zones, and I showed us that there are different methods to which you can use to create our zones. There are interactive selection, we have our interactive selection in creating zones. We have our quick zone creation, we have our advanced zone, creation. These are in zonation track. But I told you that for beginners, we are going to use our quick zone creation in actually creating our zones, which we actually did in our last class. Now, after this is the advanced way you can get the zone creation. If you need if you need the slides of this training, I'll be willing to give it out to you. Just that the organizers have not requested for it. I will send it across to the organizer. You can meet them for this slide. I'll send the PDF file of the training slides so that you can actually go through it. So as for it to help you in answering some of the questions in your assessment. Now that's just that. Now today I'm going to show us on how we can go about using our data editor. Our data editor. We're going to see how we are going to use our data editor. Now, these are conventional well log. After data QC and pre-computation, we actually went ahead to calculating our shear volume, our total and effective porosity, our formation water resistivity. I did not show us how to use the Picket plot in TECHLOG. You are going to use the Picket plot when you have your temperature data available, but we don't have that. So we went ahead to calculate our water saturation, and we also did some summaries so that we can be able to view those petrophysical parameters we've actually estimated. Now, this is just how our data selection window looks like. Our data selection window is actually what helps us carry out our computation. Now, this is our workflow manager, how it looks like, so that when you come across them, you actually know the name. These are quantity data preparation. Now, if you want to estimate your or carry out your temperature computation, this is where you come about that. And so we actually did some shear volume computation, and I showed us how we can go about our shear volume. If you click on the combined method, it's going to actually take all the well logs that you've provided. It's going to estimate your shear volume for those well logs individually, and at the end, it's going to give you a final average of those individual well logs. Using any method of your choice, it can give you you can use an arithmetic method in estimating your final average shear volume. You can use your minimum method. You can use your maximum method. There are several methods in estimating your view shear volume. That is your final view shear volume, which I have here. I have a single method to compute shear volume from several equations along with a final shear volume. That's when we're using combine. What it's going to do, it's going to estimate shear volume for the individual shear volume method and a method to compute the final, which is also there. So you should just take note of that. Now, this is just the normal computation on which we can go about our shear volume, which is our volume of shear is our GRO minus our GRO minimum. This our GRO minimum is for our sandstone, and our GRO maximum is our shear line. So you should take note of that. And we also have different parameters or different correlation in estimating our shear volume. Take note, this equation here is called our gamma ray index. Most times it's been taken as shear volume, but in some field we have some numerical correlations that helps us get a good estimation of our volume of shear. We have the Larinoff tertiary rock estimation, and this is what we use for the Niger data, because this actually gives us the minimum shear volume in order for us not to cut off some important area or some important thickness of our sandstone formation. Because the higher your sandstone, the higher your shear volume, the lower your sandstone formation. Because your sandstone formation or your quartz formation is actually your one, which is the whole minus your shear volume. Whatever it gives you the thickness or the volume of your sandstone. So if you overestimate your sandstone, that means you are getting rid of some thickness of your pay zone. So in order for you to get a better correlation, we actually go with the correlation that actually gives us the best minimum average of our shear volume, and Larinoff tertiary gives us that for the Niger Delta. Now this is how we compute our shear volume. This is the plot of our shear volume. Now this is when we use our combined method. The combined method, this actually where the final shear volume is being calculated. All these other ones are for different logs. This can be for your gamma ray, this can be for your density, this can be for your sonic, this can be for your neutron porosity, and other this can be for your resistivity. All other logs can be used. But after these logs have been estimated individually, after your volume of shear have been estimated individually by this log, your software will now run the average, which is all this for you in order to give you your final average volume of shear. This is using your combined method. Now we have total porosity computation where we have our total and effective porosity. And I told you that porosity is classified based on the engineering aspect and the geological aspect. Using the engineering aspect to classify, or the engineering point of view to classify your porosity, you'll be looking at porosity as total and effective porosity. While when we are considering porosity from the geologic point of view, we are looking at porosity as our primary and secondary porosity. So here we are actually looking at our total and effective porosity, and ways to compute our total porosity is here, and ways to compute our effective porosity is also here. Note, for you to have your effective porosity is to remove the volume of shale you have in your total porosity. That will give you the volume of your connected porosity, which is your effective porosity. Effective porosity is actually our connected porosity. Then we did some saturation computation. Uh, these are log visualization and so so that is just all we did. So today we'll be going straight to geomechanics computation, geomechanics computation. So at this point now, I would just like you again to hit up the chat box so I can get your reactions and feedback in in your in your understanding so far, how you have actually understood the course so far, if it's going fine with you, and if you are having any challenge running the same or following the workflow in your own personal software or in your workstation or your school workstation. If you're having any kind of challenge, please at this point I would like you to know that just hit up the chat box before we continue. Thank you.
Sir, I think we don't have questions, so you can
Please
continue.
let other people, let others. We have about 23 participants. Please, for me to know if they're actually with their system or they're sitting in front of their system, I won't want a situation just where one person is reacting. Please, I would like others to react. Let it be that most persons are not just coming for the certificate of participation. So please, if you are seated in this class, please tell us how far you've been able to understand this course, or if it's difficult, if you're having any form of challenge, tell us the level of assimilation so far. Thank you. Okay. Uh, I think we'll continue and we'll proceed with the training. Now I'm going to share my screen, my software screen. Okay, back to training. Now we're going to go through geometric computation at this point. And to start that, we'll be working with just our PL4. Now I'm going to take us through our well logs that are available. Now doing your geometric estimation, we'll be using our density log. That is our, sorry, I say density, our sonic log. This is our DTC. This is our sonic log. Compressional sonic log. Now we'll be using our compressional sonic log to estimate our VP, our primary velocity, and from our primary velocity, we're going to estimate our secondary velocity. The explanation to all these are in the material I'm going to send to the organizer. So I'm still going to take us through all that so that we can actually understand the concept of reservoir geometrics. So starting with this, we're going to check how we can convert from our compressional velocity, our compressional sonic to our VP being our compressional velocity. Now, if you look at if you look at the unit for our compressional sonic, you are going to see that the unit is microseconds per feet. Now, you should know that our velocity is in either meter per foot or is in kilometer per foot. Now, if you know this, you see that to convert from our DTC to our VP, we are actually going to do the inverse. We are going to do the inverse of our DTC. And in order for us to do that, we are going to be using our calculator in RockDoc, in TECHLOG. So to do that, we are going to come to our data. You are going to see your data editor. You click on it. Then you are going to select your DTC. You left click on it. You drag and drop. Here, here is the log. So any kind of calculation that we want to do can be done here. So what we're going to do now is to estimate our VP. Estimating your VP, what you do, you come here, you type in your VP, capital V and small p. Now,
Sir,
yes, sir.
I think your screen is blocked.
My screen is what?
It is blocked. We can. I'm not seeing what you are doing. So if you can reshare it or.
Can you see it now?
Yes, we can.
Okay. So do you think I should redo what I've done? Hello?
Yes, we can see it.
I'm asking, do you think I can redo what I've done so far?
If you can just repeat.
Okay. Okay, let me just close this up. Okay, what I did, I said in order for you to carry out any kind of calculation in your TECHLOG, you come to data and you come to data editor. If you bring out this interface for you, and what you do, you are going to estimate your by bringing once you bring in this to show in this format. So all you just need to do is to type in your VP here, and where you have this equal to, here's where you are going to put in your equation. So the equation for estimating primary velocity is the inverse of the TC, and our primary velocity should be in kilometer per second. So in order for you to do your conversion from this microseconds per foot to kilometer per second, the conversion factor is 306.5 all over your DTC. So you just come here and click on your DTC on this heading. If you select the whole column, and what you do, you click enter. Once you click enter, I see that our VP log have been selected. Now we have to estimate our VS, which is our shear velocity. Now your shear velocity, we estimate our shear velocity using a correlation, which I'm going to type for us now so that we can actually get it. So I'm going to show the correlation we'll be using in our VS estimation. Please just give me a while I bring it up. I'm trying to bring out the correlations for the Niger data. Okay, the correlation for the Niger data is Castagnar's equation. So Castagnar's equation. Okay. Okay, Castagnar's equation says VP log is equals to 1.16 Vx log plus 1.36. So that's our Castagnar's equation. So all we're going to do now is to bring in that value or that equation into a plot. So I'm going to come here. I'll clean out this. I'm going to clean out this, and I'll change this other plot to VS. Okay, before this can run, we are going to actually close this up. You see, do you want to save the modified variable? You click on yes. Then you are going to see VP shown here, but our VP that is shown here is graded out. Our VP is graded out in this place. So what you are going to do is to actually make this bold. You can do that by selecting it. If you select it, you come to your properties, as I've showed us earlier. You come to your properties and you click on where you have your unit. Click on the drop down. It's not showing. You come to your compatible list. You are going to see kilometer per second. This is it. You click on kilometer per second, and I see that the thing now is bold. So that's how we come about that. So the next thing we are going to do now is to go back to our well log editor, our data editor. If you're in your data editor, you are going to bring in that Castagnas equation for estimating secondary velocity. So I don't know if anybody copied that velocity. Please give me a little while. Let me bring it up again. Okay. Okay, the Castagnas equation that we'll be using for the Niger data, we'll drag in our VP log. Once we bring in our VP log, we'll type in here our VS is equals to our VS log for Castagnas is 3.7 minus 6.3 times velocity porosity. Sorry. 6.3 times. I'm going to bring in my porosity log, my effective porosity, times my effective porosity, bracket close, minus 2.1 times my volume of shear times my volume of shear. I'll close up the bracket and I'll click on enter. So this is my VS. I will scroll down to check the values. Okay, I have the values in some part here. This is the value of my VS. So what I'm going to do is to estimate for my shear sonic. What I have before was my compressional sonic. So I'm going to estimate my shear sonic velocity, and my shear sonic velocity is the inverse of my shear velocity. So converting it from kilometer per second to feet to microseconds per feet, we still use the conversion factor 306.5 divided by VS. Come here, we click enter. So this is giving us a shear sonic. I see it. So we're having a shear sonic, we're having a VP, and we're having a VS. So all you just do now, you tend to close up this workspace. You see, do you want to save the two modified variables? The two modified variables are the X log and the TS log. So I'll click on yes. Now, if you come to your project browser, you are going to see those variables here. You are going to see your VX log. Your VX log is not having any unit. So we assign unit to it by selecting it, coming to properties. We'll go to compactable list and select a kilometer per second. Once you select that, it will now be good. You also come to your TS log. You see that it's graded out. You select it. You come to your properties. You come to your compactable list. Now, this is in microseconds per foot. So this is it. You select and you click OK. So that is how we go about estimating compressional velocity, shear velocity, and shear sonic. So that is how we go about that. Now, the next thing we are going to do is to go ahead to estimate some of our geometrical properties. If we come over to your Geomechanics tab, we are going to start with our elastic properties. So there's a drop down. You click on the drop down of your elastic properties. You are going to see your dynamic properties. Now you are going to follow this. This is just the workflow for you to go about your reservoir geometrics. The first property you have to estimate is your dynamic properties, your dynamic elastic properties. We have our dynamic elastic properties, and we have our static elastic properties. So click on the dynamic elastic properties. It will bring in this. You see that it's requesting for our compressional slowness. Our compressional slowness is the TS, which we estimated. This is the TS. The TC is a compressional slowness. Our shear slowness is at the TS, which we've estimated. So we're just going to go to log, and we search for the T. These are the TS. Push it in. These are the TC. Push it in, and we click on create. So I think I've closed that. Okay, something is going on. So one or more variables are missing. Okay. Now there's actually an error here. Our VP and our VS log, they are supposed to be in our logs. Topic properties. These are compressional slowness. Density here is Okay, it's not in Aru HOD, it's in dense. So that is the error it is popping out. So I'm pushing the dense and I'll click concrete. Okay, this is it. Isotropic properties for PL4. So what I'll do now, I'll click on save and display, and I'll click on. So now you see we are having a GC, we have a SMG, that is our shear modulus dynamic. We have our Poisson's ratio, and we also have other elastic properties. These are the properties estimated. These are bulk modulus dynamic. These are Poisson's ratio. This is our shear modulus estimated, and I think one other one. And these are Young modulus. These are all the dynamic properties, dynamic elastic properties. You know what elastic properties are? We have our Young modulus as an elastic properties. We have our shear modulus as our elastic properties. We have our bulk modulus, and we also have our Poisson's ratio. So the next thing you are going to do is to calculate your static properties. And you start by calculating static Young modulus. After you've calculated the static Young modulus, you go ahead to calculate your static Poisson's ratio before we use these parameters estimated to calculate our varied coefficient. Now, if you've done this, we'll come over to our static modulus. We're going to use our John Fuller method, and it's requesting us to input our Young modulus dynamic, which is our Y to Y. Here we're going to see our Young modulus dynamic. We push it in, we click on create, we close this up, enlarge this. These are Young modulus dynamic, which we want to use to estimate our Young modulus static. So we're going to click on save and display. So it has estimated our Young modulus static using our John Fuller correlation. So we've succeeded estimating our dynamic Young modulus and our static Young modulus. So we'll come again to estimate our static Poisson ratio. There is requesting for our dynamic Poisson ratio, which is our V arrow dynamic. We push it in, we click on create. So this is it. We come here, save and display, and we click on play. So it has estimated our Poisson's ratio static. Poisson's ratio static. This Poisson's ratio, the unit is unitless. So if we've done that, we'll come again. We've estimated our Poisson's ratio. So we are going to estimate our static bulk and shear modulus. Take note, we've estimated our static Young modulus. So here we're estimating our static bulk and shear modulus. So we're going to push in our Poisson's ratio static and our Young modulus static. This is our Poisson ratio static. So our Young modulus static, we use our John Fuller's method. We'll push it in. I'll click on create. We'll come here, save and display. We click on play. So I see we have our shear modulus static and we have our bulk modulus static. So we will now come further. We come here, our elastic properties. We'll come to our varied coefficient. We use our groove porosity to estimate. Now it's asking us for our effective porosity. We come here, we're pushing our effective porosity. Our porosity effective. That's poro E. So push it in, we click on create. I will come here and click on save and display. So if you click on play, you are going to see your varied coefficient estimated here. So I'll just give us a minute for those of you using your system to actually meet up to speed if there is anywhere you are lagging behind. Thank you. Okay, back to where we stopped. So we've estimated our elastic properties. We are done with our elastic properties. The next we are going to go into is our rock properties. Now, rock properties are rock strength properties. We have our unconfined compressive strength, we have our cohesion, we have our friction angle, and we have our tensile strength. So for our unconfined compressive strength, we are going to use this Coates correlation. You click on Coates correlation, it's asking us for our shear volume, our Poisson's ratio dynamic, and our Young modulus dynamic. It's already pushed in by default. We click on create. We come here, we click on save and display. So if you check here, you see your UCS, there's uncompressed compressional stress. So we'll come back. There's unconfined compressive strength. We'll come back. We've calculated this, we'll come to our cohesion. But if you check here, you see cohesion from your UCS and friction angle. That means we have to calculate our friction angle first before going back to our cohesion. So we are going to estimate our friction angle. These are different correlations used in estimating friction angle. But here we're going to estimate our friction angle using our GRO log. So we're going to push in our gamma ray log now. We're pushing our GRO log. Click on create. Come here, click on save and display. So this is my friction angle from my GRO log. I have my friction angle from my GRO log. So the next I'm going to do now is to go back to calculate my cohesion. So I'll come now and click on my cohesion from UCS and friction angle. So I'm going to bring in my friction angle, which I just estimated now. I'll bring in my friction angle. This is my friction angle from GRO. And I'm going to bring in my friction, my unconfined compressive strength, which is my UCS. I'll push it in. I'll click on create. I'll come here, I'll click on save and display. I've estimated that by cohesion. Now, lastly, I'll come here and click on my tensile strength from my UCS. It's already pushed in by default. I'll come here, I'll click on save and display. So this is my tensile strength. Now, this is how we go about estimating our rock properties, elastic properties. Now, finally, I'll show us how to go about our stress estimation. You go about your stress estimation, coming to your horizontal strength, where you have your minimum and maximum horizontal stress gradient. You have your maximum horizontal strength. Take note, this is the gradient and this is the stress itself. And you have your stress calibration, which we are not going to do. So we're going to estimate the gradient using our more column stress model, which requires us to push in our vertical stress and our pore pressure. But since we've not estimated our vertical stress and pore pressure, we cannot be able to go further on this. So that's where we'll be ending for our geometry. It is in our workflow how to estimate our elastic properties and our rock strength. Now, maybe those of us that are interested taking it further, you can hit my LinkedIn page. We'll discuss on how we can actually go further on estimating log pore pressure of our body stress before we go back to our wearable stability. Then we can be able to generate our 1D mechanical health model. But this is beyond the scope of our study. So thank you very much. At this point, I would like to know if there's any question or any comment. Thank you.
Okay, thank you, sir. I think we don't have questions. So thank you, Mr. Chukwudi. I think we are at the end of our session and of course at the end of our TECHLOG training. Thank you for participating in our event and wish you a very good evening. Thank you, everyone.
Please, I'm waiting for our comment and reaction. If there is none, please over to you, coordinator.
Sir, I think we don't have questions.